In this lesson, we are going to look at the constant e, one of the most important constants in mathematics, and the natural logarithm, the logarithm that has as a base this number e. We will try to understand the nature of number e and where from it comes. Number e, if you want, is similar with the number pi in mathematics. It's a constant that occurs naturally from some phenomena that we see around us. And they are related it is related to natural growth. We are going to look again at the graph of e to the power of x and its inverse graph, ln of x, which is log in the base e of x. We'll learn about this notation. Now we can introduce e into different ways. First, it's a bit mechanical, and second, I'm going to try to see you how it appeared. So if you look at the mechanical way of introducing it, look at your calculator, and then you can see a button which is labeled e or e to a power. If you press this button, just the button e, or if you have e to a power and then you type 1 in the box, which is basically e, you will get an answer which is 2.71828 and so on. E is an irrational number, same as pi, meaning that it has an infinite number of decimals that are not repeating. You might ask yourself a very good question at this point, why this number and not another? Why this sequence of decimals? And I'm going to get back to that in a moment. Now, as the function f of x is e to the power of x and is similar to 2 to the power of x, 3 to the power of x, just the base is another number. Related to it, the graph is that one, similar to 2 to the power of x, because as you see, e, it's a bit bigger, so it's bigger than 1. Related to it, we have the function, the logarithmic function, and the logarithmic function is, I can call it f minus 1 of x if you want, it's an inverse of the one above, is log in the base e of x. Now, because this logarithm is very, very often met, we have a notation for it. We denote it ln x. So when we see ln x, we know that in fact it is log in the base e of x. So that's a notation for it. You'll see on your calculator another button called log of x with no base. It's a convention that log x is actually log in the base 10 of x. Try to press in your calculator log 10 and you see that you get 1. Because this base is implicitly 10, so 10 to the power of 1 is 10. Try to put in your calculator ln e squared, and you are going to see that you get 2, meaning that this base is e without being there. So that's a very simple and mechanical way of introducing e. Let's look on the next page as how it appeared in mathematics. Now, if you are happy with learning things mechanically and getting only fluency, you can stop at this point and try exercises from your textbook. However, I think it would be a loss because the whole beauty of maths comes from the fact that it makes sense and all comes together and all is derived from one concept to another. So that's why I think you lose a lot from understanding the nature of math and perceiving its beauty if you stop here. You have a choice though. We plotted in GeoGebra two graphs, y equals to the power of x and y equals 3 to the power of x. Let's call them the green and the red graphs. 2 to the power of x and 3 to the power of x. 3 to the power of x is steeper. Now, I took two points A and B, A on the first graph and B on the second graph, so that their x coordinates are the same. We can compare them. When I change the slider, the points will slide along the two graphs. At each point, let's take point A, I drew the tangent to the graph, and it's a red line here, so that we can look at the slope of the tangent. Remember that the slope of the tangent is a derivative of the function. So how steep the tangent is gives me the derivative. So this number here, 3.08, is a derivative of 2 to the power of x at x equals 2.05, 2.15. We didn't study yet the derivative of exponential functions, so that's an introduction to them to see where from the number e comes. Now, let's start the movie and watch what happens. I'm going to use it to collect some data that I'm going to write on the next page. So I'm starting from the left with A and B. While I move them across at x equals 0, these are the two slopes of the two graphs. And then at x equals 1, these are the two slopes of the two graphs. And then I move to x equals 2 to find the slope. And at x equals 3, again to find the slope, and so on. And I'm going to write all the slopes or the derivatives on the next slide. Now, in order to be more accurate, instead of taking the derivatives from the movie above and from the graphical representation, I also used a calculator that will give me the values. So the derivative of 2 to the power of x when x equals 0 is 0.693. Let me take 3 significant figures. Then it's 1.386, 2.772, 2.773. I'm sorry, I don't see very well. And for x equals 3 is 5.545. I'm going to do the same for y equals 3 to the power of x. What is very interesting to see that when I move from 0 to 1, the number gets twice as big. And from 1 to 2, the number or the slope gets twice as big. And here gets twice as big. You can try. You'll see better if you look at these more accurate numbers, how the slope, it's increased by 2 every time. When I look to 3 to the power of x, it's times 3. Times 3 and times 3. Now stop a bit and look at what we have here. So when we keep from 2 to the power of x to 3 to the power of x, at x equals 0, the gradient or the slope is smaller than 1 and here bigger than 1. Therefore, it must be a number between 2 and 3 here, right? Because I can grow these numbers continuously, such that this slope here is 1. Right? Because the increase is gradual. Now, as we have 2 to the power of x, the slope increases 2 times, 2 times, 2 times. For 3 to the power of x, the slope increases 3 times, 3 times, 3 times. Therefore, if I have here a base, and I'm going to call it e, the slope will increase e times. So I'm going to have e squared, and here I'm going to have e cubed. So it must be such a function that fulfills all these properties. Therefore, we have a new number, e, such that the derivative of e to the power of x is always e to the power of x. See, the derivative of e to the power of x at x equals 1 is e to the power of 1. At x equals 2 is e squared. At x equals 3 is e cubed. Therefore, we found a new number e such that the derivative with respect to x of e to the power of x is always e to the power of x. That's one of the properties of the new number e. But what is it exactly? We're going to see how do we find this value. We're going to see this on the next slide. So on this slide, we saw that such a number must exist so that the derivative stays as it is. On the next slide, we're going to find the value of number e. How does my calculator find it? So we're going to ask ourselves, what actually is a value? How do we find this 2.71 at the k? Right, we have a new function, f of x equals e to the power of x. We know that the derivative to e to the power of x stays as it is, but we're going to leave this property for a while. We're going to come back to it in the unit on derivatives. Now, what's that new function? So my question would be, can it be a polynomial? So is e to the power of x a polynomial, or is it a different type of function? Yeah, we see that it's an exponential, but I'm thinking, can it be also a polynomial? So let's assume that it can be a polynomial, or it is a polynomial. Therefore, it means that I can write e to the power of x at a0, the free term, plus a1x. A polynomial looks like this, a2x squared, a3x cubed, plus, and so on. I don't know where to stop, an x to the power of n. It continues, yeah? So it will stop at an x to the power of n. I'm not going to write this last term because I don't know exactly what n is, so therefore I will leave it like this. Yeah? But in this needs to be true for all x's. For all x's. Okay, let's take x equals 1. Let x be 0, sorry. So e to the power of 0 needs to be a 0. a1 times 0 is 0, a2 times 0 squared, so all these are 0. So therefore, a0 needs to be 1, because any number to the power of 0 is 1, so e to the power of 0 is 1. So we found that e to the power of x is 1 plus a1x plus a2x squared plus a3x cubed plus so on. I need to find a1 now. I need to find the coefficient such that I find the polynomial. So we are going to differentiate both sides with respect to x. And we saw that the derivative of e to the power of x is e to the power of x. So e to the power of x is the derivative of 1 is 0. So I get a1 plus 2a2x plus 3a3x squared. Let me write one more because I'm going to need it later, plus and so on. So now, as you can imagine, I will put again x equals 0. It's a trick to help me find a1. So e to the power of 0 is a1 plus 0, all these terms are 0. So a1 is 1 itself. Therefore, e to the power of x is 1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus and so on. I'm going to let x 0 again. Oh no, sorry, I'm going to differentiate first. So again, the derivative of e to the power of x stays as it is. 1 disappears, so I'm going to have 2a2 plus 3 times 2 a3x plus 4 times 3 a4x squared plus and so on. And let again x equals 0. So we're going to find that a2 is 1 over 2. Wow, that becomes interesting. So e to the power of x is 1 2 times a2 plus 3 times 2a3x plus 4 times 3a4x squared and so on. So differentiate again, and we get e to the power of x equals 3 times 2 times 1 times a3, if you want the derivative of x is 1, plus 4 times 3 times 2 a4x plus so on. Again, let x equal 0. You might want to pause the movie and try yourself. So e to the power of 0 is 3 times 2 times 1 a3. E to the power of 0 is 1, so you see how a3 is 1 over 3 factorial. Let me keep this notation because the numbers get bigger and bigger. Differentiate this again to find a4. So we get e to the power of x equals, this one disappears because there's no x. So this term is going to give me 4 times 3 times 2 times the derivative of x is 1, a4. Again, take x equals 0, so a4 is 1 over 4 factorial. And as you see, I can continue, and it will never end the process. So going back to my initial equation here, I found a1, a2, a3, a4, and so on. Sorry, that's not this one. That was after differentiated. It's going to be the first one, this one. And now I found a0, a1, a2, a3, and so on. So I'm going to replace there. And I'm going to write my answer here. Therefore, I found that e to the power of x is a1 plus a0 plus a1x plus a2 x squared plus a3 x cubed plus a4 x to the power of 4 plus and so on. Now, because I want to see symmetry, I'm going to put 2 factorial under 2 because it's 1, and I can put here 1 over 1 factorial. So that's e to the power of x for all x's. So whenever you want to find e squared, if you take x equals 2 and you compute all these terms and you add them up, you find an estimate of e to the square. You can't find the exact value because there are infinite number of terms. If you continue the process, it will never end. So it's an infinite number of terms. Now, how do you find, our question was, what is the value of e? E to the power of 1 will be 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus and so on. Of course, I can't find the exact value of e because these terms never end. But as you see, they get smaller and smaller and smaller. That's why I can find a good enough estimate if I add enough terms. So here is an estimate for the value of e. We said that e, we can obtain the exact value if we add this infinite number of terms, but of course we can never add all these terms. So let's start to estimate it. If I add all until 5 factorial, I get this estimate for e. If I add one more term, see, it's growing a bit, but it's still very close. If I add another one, I get a bit bigger, but to 3 significant figures or even to 4 stays the same. If I add one more to 1, 2, 3, 4 significant, 5 significant figure even stays the same. So as you see, the terms that are added are smaller and smaller. That's why we can consider that that's a good estimate of e. So that's how the value of e is computed. Now that's a lot of heavy maths there, but this shows you actually that in maths nothing comes up as a surprise. All things come together and they join together into a big picture of mathematics. There are many concepts involved in the explanation of E, but that's a very good revision of those concepts. So you might take a pause and think about them and make some notes. We're going to go back to the derivative of e to the power of x in the respective unit later on in the year.